Welcome and thanks for joining this presentation on neuroadaptive gamification, where brain-computer interfaces meet interactive design. In the next minutes, we'll explore how real-time neural signals can reshape game mechanics to boost engagement, learning, and mental health outcomes, and we'll outline key findings, technical challenges, and research directions for bringing these systems into practice. Here we define neuroadaptive gamification as the fusion of BCIs and game design to adapt experiences based on neural signals, often using EEG to infer cognitive and emotional states. Unlike fixed reward systems, these approaches enable continuous dynamic tailoring, with the goal of improving engagement, learning, and mental well-being through real-time brain-system interactions. Despite exciting promise, several research gaps remain. Most studies are short lab experiments that don't reveal long-term effects or adherence. Metrics vary widely, so comparisons are difficult. EEG dominates while other modalities like FNIRs are underexplored, and real-world deployments are limited, restricting broader impact and translation beyond controlled settings. Our review focuses on three thematic areas: empirical EEG and cognitive research that examines neural markers in closed-loop BCIs, VR, and mindfulness applications that use gamified, immersive environments with real-time neural feedback, and neuroadaptive technologies that propose frameworks and systems for adaptive, closed-loop engagement in interactive contexts. We followed a systematic, PRISMA-guided methodology to ensure transparent and reproducible coverage across clinical, technical, and cross-disciplinary sources. Searches spanned PubMed, IEE Explore, Scopus, and related databases, prioritizing primary empirical studies that combined neuroadaptive gamification with real-time BCI methods, while excluding reviews and meta-analyses to focus on original findings. This PRISMA flow summarizes how we identified, deduplicated, screened, and assessed studies before inclusion. After removing duplicates, we screened titles and abstracts for real-time BCI or gamification focus, then performed full-text reviews to exclude insufficiently neuroadaptive work, and finally selected the studies that met eligibility for detailed analysis. We identified several biases and limitations that affect reliability. Language bias favors English publications. Modality bias reflects an EEG focus over other neuroimaging methods. Algorithmic bias raises concerns about model generalizability, and mitigation required broad database searches and human review. So findings remain relevant but should be interpreted cautiously given these constraints. Research activity in neuroadaptive gamification has surged recently, with a sharp increase in publications since around 2022 linked to advances in consumer EEG hardware and real-time machine learning. A dip in 2019 to 2021 suggests slower adoption then, but the current trend points to accelerating commercialization and growing research momentum as tools and methods mature. Emerging subdomains split into publication trends, research focus areas, and field gaps. EEG studies are increasingly prevalent, VR and mindfulness maintain steady presence, and neuroadaptive work is still nascent. Research emphasizes biomarkers and immersive environments, while the field needs standardization, scalable systems, and harmonized protocols to move from proof of concept to robust deployment. Non-invasive EEG enables closed-loop adaptation of gameplay to cognitive and affective states by tracking neural signatures and feeding them into adaptive systems. These setups create bidirectional brain-system interactions that adjust mechanics to optimize engagement while aiming to avoid cognitive overload by carefully timing and personalizing feedback and rewards. EEG can guide emotion regulation and feedback across applications like mindfulness, emotion recognition, adaptive stimuli delivery, and clinical relaxation support. Systems commonly detect alpha or other spectral markers to provide real-time reward loops, modulate visuals or sounds to match states, and use feedback to reinforce relaxation or teach users how to self-regulate neural patterns. Combining VR with BCI supports adaptive relaxation by reducing distractions, increasing presence, and tailoring the environment to neurophysiological signals. Immersive neurofeedback can demonstrably improve anxiety and stress outcomes, offering clinical value through measurable signals and experiential immersion that together support sustained mindfulness and therapeutic gains. Biofeedback augmented VR couples EEG and physiological metrics with gamified interventions for anxiety, meditation, and chronic pain. Clinical applications range from EEG-driven relaxation to neural biofeedback in VR, targeting adults with anxiety disorders, stress reduction seekers, and chronic pain patients, and showing promise for improving adherence and symptom modulation through interactive feedback. Balancing EEG reliability with VR immersion presents technical trade-offs. VR headsets introduce artifacts that degrade EEG quality, artifact removal can impact immersive fidelity, and the core challenge is preserving presence while maintaining signal reliability. Existing mitigations help, but robust protocols are still needed to measure how VR presence interacts with feedback effectiveness and standardize best practices. Neuroadaptive architectures typically include layered stages: low latency signal processing to acquire and clean neural data, ML classification to label cognitive states, feedback control to apply personalized adaptations to gameplay, and an adaptation spectrum that ranges from reactive adjustments to predictive anticipatory modifications that optimize engagement over time. Predictive and proactive models shift systems from reactive responses to anticipatory adaptations by using CNNs, LSTMs, and reinforcement learning to forecast user states and optimize reward schedules. These approaches reduce latency limits of classic BCIs and enable timely game modifications that improve engagement and the effectiveness of interventions through early personalized adjustments. A technology taxonomy maps components like signal processing, machine learning, feedback mechanisms, and system architecture to concrete implementations and adaptation strategies. Robust filtering and low latency pipelines, online model updates, reinforcement learning-based reward shaping, and modular APIs are all part of building scalable, synchronized, closed-loop BCI VR systems. Computational and ethical challenges require careful balancing. Hierarchical models trade off speed and fidelity, many interacting variables complicate rapid adaptation, and opaque neural adjustments pose ethical risks to user autonomy. Future priorities include improving interpretability, preserving user control, and implementing explicit transparency safeguards while maintaining efficient adaptive performance. At its core, neuroadaptive gamification forms a closed-loop bridge between mind and system, where continuous feedback reshapes cognition and behavior. These adaptive experiences assemble momentary cognitive and emotional states into personalized learning or therapeutic puzzles, enabling interventions that respond to users in real time and support individualized outcomes. Methodological limitations and publication bias complicate interpretation. Varied metrics and adaptation measures make cross-study comparison difficult. Positive outcome bias can overstate effectiveness, and a dominant EEG focus narrows insight into other modalities. Moving forward, combining findings cautiously and expanding methodological diversity will strengthen conclusions and generalizability. Actionable research directions include running extended duration studies to assess long-term effects and variability, developing standardized metrics and protocols for consistent evaluation, integrating multimodal neural and behavioral data to boost reliability, designing transparent user interfaces to build trust, and aligning research efforts to harmonize duration, metrics, and UI design. To conclude, EEG-based neuroadaptive gamification personalizes gameplay to brain signals, transforming static experiences into responsive, therapeutic, and educational systems. Immersive VR amplifies these benefits, but realizing scalable, precise, and transparent systems requires addressing technical, methodological, and ethical challenges so that these tools can deliver broad societal impact as they mature.